In this video, we're going to look at how to sketch the truncus. We'll start by looking at the overall shape of the truncus and how each of the terms impacts that shape. And then at the end, we're going to look at an example of how we can sketch it by hand. For those who don't know me, my name is Chris Iannazzoni. I used to work as an engineer for a defense company, and I've since left that to start a career in tutoring. I make these videos so that VCE students can do the best they can in math methods. With that out of the way, let's get into it. The general form of the truncus is as follows. You'll notice that the shape of the truncus is very similar to that of the hyperbola. The only major difference is that the negative half of the hyperbola is flipped to become positive. We can see this in the function because the denominator is squared, removing any negatives. The a term in the numerator is known as a dilation factor from the x-axis. If a is larger, then the graph is going to get further away from the axes. If a gets closer to 0, then we actually observe the graph to get closer to the axes. The b term is very similar. It works in the opposite direction to a. So if b gets larger, we get closer to the axes, and if b gets closer to 0, then we get further away from the axes. Reflections are identified as a negative sign applied to the truncus. The good news is that only a reflection in the x-axis is possible for the truncus. This is because the truncus is naturally symmetrical about the y-axis. We see this mathematically because our denominator is squared, thus removing the possibility of a negative. The last thing we look at are the translation factors, h and c. These are responsible for shifting the graph horizontally or vertically. Horizontal translations are determined by the h term. If you have x minus h, then you are shifting your entire graph to the right by h. In this example here, we have x minus 2, meaning that we're shifting the entire graph to the right by 2. In the case of the truncus, you can think of this as shifting the location of your vertical asymptote. If you instead had x plus h, then you would be shifting the graph to the left. In this example, we have x plus 1, meaning we're shifting the entire graph to the left by 1. Vertical translations are determined by the c term. If you have plus c, then you're shifting your graph upwards. In this example here, we have 1 over x squared plus 2, meaning that we're shifting the entire graph up by 2. In the case of the truncus, you can think of this as shifting the location of your horizontal asymptote. If you have minus c, then the graph is going to move downwards. In this example, we have 1 over x squared minus 1, so the graph is shifting down by 1. So, when it comes to sketching the truncus by hand, there's only 3 things you need to know. The asymptotes, the axis intercepts, and the endpoints. We use the following framework to help us with that. Let's check an example. To start with, we want to make sure that we're starting with the general form of the truncus, because that'll make identifying all of the key features much easier. In this case, we just need to take the coefficient off of the x. And in the case of the truncus, we can even take it out a step further by taking it outside of the squared term, although this isn't strictly necessary. From here, we can easily see where the asymptotes are. The vertical asymptote is dictated by the horizontal translation, so we're going to have a vertical asymptote at x equals negative 2. And the horizontal asymptote is dictated by the vertical translation, which is going to give us a horizontal asymptote of y equals 2. Now we move on to solving the axes intercepts. When it comes to the x-intercepts, we start by subbing in y equals 0 and then rearranging. In this case, it's going to require us to square root both sides of an equation. You might notice that we just tried to square root a negative number. That's your indicator to realize that this truncus has no x-axis intercepts. Oddly enough, it's pretty common for a truncus to not have x-intercepts. In fact, the default truncus has no intercepts at all. Y-intercepts, however, are much more common. In this case, we're subbing in x equals 0, and after some simplification, we see that we indeed do have a y-intercept. The next step in the framework would be to find the endpoints. In this case, we don't have a restricted domain, so this isn't going to be applicable. We can move on to the next step, which is just sketching. Now that we have all of our key features, we just plot them on the graph and then draw our curve connecting all those key features. If there is a restriction on the domain, then all you're going to do is sub in the lower and upper bound of your domain into the function, thus getting the corresponding y values at that spot. Once you have those coordinates, you're just going to cut your graph off early between those 2 spots. Just be mindful of the brackets. If you have a square bracket, that means you have a full circle. If you have a rounded bracket, that means you have an open circle. If you found this video helpful, then you should consider joining my free community. I host a Q&A call every week to personally help you through any of your specific questions, and you'll also get access to more resources like this, including written and recorded lecture content, as well as practice exams and SACs with detailed solutions. It's pretty cool, you should check it out. I'll see you there.